Integrated Circuit 5, Analog Circuit, Op-Amp, Part 2. Now, we talk about some consideration for making an Op-Amp on a silicon chip. We are not making an Op-Amp using a discrete component. The critical design issue is this emitter resistance and collector resistor. The VBE1 and VBE2 characteristic has to be identical to eliminate the drift issue. To do that, we make a twin transistor like this. Layout becomes very important. Okay, collector well, two collector well side by side, and the base P doping for the base side by side, and emitter identical size. And even there is a slight misalignment on the emitter, it's going to affect both emitters same way. So this kind of positive correlation the positive means when this shifted this way, this also shifted, so characteristic will be still tracking same way. Okay, so we use the characteristic of correlation on the IC chip manufacturing. Next one is N plus determined RE, and this is critical to the gain of op-amp. So for analog circuit, the IC chip processing, we have to consider relatively high N plus doping for emitter. The both RC and both RC, this guy, are made in parallel, close together. So this also, the resistor is the resistor well on the silicon chip. Put both of them together side by side and make sure they are tracking, their value is very much like almost identical. So the layout is critical in analog design. And control IS, this guy, for multiple IP op-amp on a single chip, we have to control this IS, and we talk about this the current source circuit later. So op-amp, the IC chip has a dual output. So the if you look at the op-amp IC chip, usually plus minus and single output, and you can feed back to this negative or positive. You can do all kind of things, but on chip, op-amp always has a dual output. Okay. For example, this is a negative feedback. The output, you divide voltage by R1 and R2 and the feedback negatively. Then it's become a single input EI. The EI minus, this will be E0 divided by gain. So equations tells us that E0 over EI, the gain is going to be given by this, right? So for example, the op-amp gain is 80 and 100 kilo ohms and 1 kilo ohm resistor combinations give kind of 10 k ohm, 1 k ohm give the actual gain of 44. We change this value 1 kilo ohm to 10 kilo ohm, it's dropped to 9.6. So this is ideally op-amp very high gain. We can reduce this into 44.9 or even 9.6. So this is the actual gain of the circuit. Gain of the circuit can be determined by the resistor R1 and R2. So this is a normal op-amp application. If you ever use the op-amp in your circuit design, this is how you control the actual gain, because G is very large and the gain is given by the resistor, determined by resistor. So depending on how much the feedback you increase, in this case R2 is a feedback. You increase negative feedback, the gain drop. Okay. High gain amplifier picks up noise easily, so sometimes you reduce the gain at the noise critical area. The positive feedback causes oscillation. So this is the regular analog design considerations, even without chip. Same as the board design, you have a PCB board, you mount the op-amp chip, then you design the analog circuit. It's basically same thing. It's you can do on silicon. Okay, so that's a kind of the technique you can learn from any analog book. Usually they talk about how to use the op-amp IC chip. Only things you cannot do is to use capacitance and the inductance. That's not available on the IC chip. Other than that, all the technique you learn from this IC chip design, you can use on chip, so silicon chip. Okay, so this is the general analog design technique. If you like, subscribe.